both of those masts are going to pull away just before launch. Quick word about the ignition sequence. We switched the engines on 19 seconds before launch. That's because we throttled them up slowly to check everything's working fine. We're coming up to the 1 minute mark. We are live at the Guiana Space Centre. We're launching Cso1 for the French Space Agency, CNES, and the French Defence Procurement Agency, the DGA, built by Airbus as prime contractor, and with help from Thales Alenia Space for the all-important optical instrument. And we're travelling on board the 20th Soyuz to launch from the Amazonian jungle, and the last launch this year from the CSG.
À tous de DDO, attention pour -1 minute.
Our best wishes to all the teams.
Top, H0 -1 minute. Largage du Macazeden. À tous de DDO, attention pour le début de la séquence d'allumage du lanceur. Top. À 0-20 secondes. Largage du Macazeden. À tous de DDO, attention pour le début de la séquence d'allumage du lanceur. 5, 6, 3, 2, 1, top. Allumage. À tout. Décollage. Les paramètres bord sont normaux. Bonne stabilisation du lanceur.
And they are off. They are off. Cso1 has started its journey.
Les moteurs du second et du premier étage fonctionnent nominalement.
Soyuz blazing a trail across the skies here at the Guiana Space Centre. Heading out north over the Atlantic. Superb images there of the boosters being jettisoned. See how they twist and turn, all part of the plan. And that's what it looks like from up there. We had cameras on a previous launch. And we're now looking at the dot in the middle there, the engine of the main stage, which is propelling us towards space. The Soyuz flying away from us. Superb images there. Very lucky to have clear skies. And he's telling us that the second stage is burning nominally. Everything is going according to plan. Top right-hand side of your screen, the trajectory. That's the trajectory of the vehicle, the planned trajectory, with the cross being the actual position of the launch vehicle. Take a look at the front of the vehicle there, the pointy section. We saw it before. It's called the fairing. Our satellite is in there. And if you work your way sort of down towards the middle section, have a quick look there, the orange section. There's an open section, an open lattice section. I'm going to tell you about that later. We'll see that in action. That plays a very important role. So the fairing was protecting our satellite from the rigors of the launch. You can just imagine how loud it was at liftoff back there, protecting us from acoustic vibrations and from friction as we were coming up through the denser part of the atmosphere. But now look at our altitude. We are 122 kilometers above the Earth, and we've actually gone beyond what we call the Kármán line, which is the border with space. And we hardly have any friction now, so we're coming up to the point where we can start the process of jettisoning our fairing, because the name of the game is to lose weight. This is the moment, the scheduled moment to jettison the fairing. We'll get the confirmation of that later. Oh, look at that. It's great, those images from previous launch. And we have confirmation that the fairing has been jettisoned, and we can see our satellite exposed to space for the first time. Now, remember that open section in the middle? It's about to do its job. It's because we use a hot stage technique to switch on the engine of the third stage before we jettison the second stage, and therefore we need that open area to evacuate. And you can see you saw back there the 4 parts of it fell away. So we lifted off from the Guiana Space Center, and we have confirmation that that's now been separated. The tracking station here at the Guiana Space Center is called Galileo. You can see it there, and you can see our flight path. The little sort of star, if you like, is our launcher, heading up towards the next tracking station, which is Bermuda. Bottom left-hand side of the screen, altitude. He's telling us that everything is going according to plan. Our altitude, 184 kilometers above the Earth. Our distance, now that's the distance as if you were to draw a straight line across the pad from the liftoff from the pad, if you like, to the point where the vehicle is over the Earth. And our speed on the bottom right.
Lanceurs sont nominaux.
Everything going according to plan. Our speed for 4 kilometers and 4.64 kilometers per second, ladies and gentlemen. Let's just say that again. We are flying nearly 5 kilometers per second, not per hour. Here's an overview of what's going to be coming up and the major milestones.
After lifting off from the Guiana Space Center, the flight of the 3 lower stages of Soyuz will last about 9 minutes. Then the upper composite, made up of the frigate upper stage, the adapter, and the Cso1 satellite, will separate from the third stage of the launcher. The 3 lower stages and the fairing will drop off into the sea. Frigate will perform 2 propulsion burns before the separation of the satellite. First burn of about 9 minutes, followed by a ballistic phase of about 35 minutes, and a second burn of about 1.5 minutes, followed by a second ballistic phase of about 5 minutes. The Cso1 satellite will then be separated on its dedicated orbit 1 hour and 44 seconds after liftoff. At the end of its mission, Frigate will be placed on an orbit safely below the satellite orbit thanks to one more ignition of its engine.
So that's what's coming up. Now, our flight path takes us north heading up over the Caribbean, along the east coast of the US. We cross the Arctic, and we come back down to the southwest coast of Australia, where we'll be starting the process of separating our satellite. The whole thing takes roughly an hour. We heard an overview of that from Stefan Israel earlier. We're using telemetry to track our vehicle. Basically, for anyone who's not familiar with that, during the flight, Soyuz sends information to the ground stations along its path, and they then send that data here to the teams at the Guyana Space Center. And this allows them to monitor the flight in real time, so that's how we get the confirmations that the range operations manager is calling out, and it also allows them to make an evaluation afterwards. So this is the scheduled moment for the third stage to burn out and be jettisoned. We'll wait for the confirmation of that.
Séparation partie haute.
And we have the confirmation that it has now been jettisoned. And we're seeing
Acquisition de la télémesure lanceur par la station des Bermudes.
And we also have confirmation that we've now picked up this signal at the tracking station in Bermuda. That's in the Caribbean ladder of islands. And we're seeing key moments happening as they are scheduled to happen at the time they're scheduled to happen. We get the actual confirmations of those from the range operations manager just a little bit later. That's perfectly normal. It's because the data from the launcher has to go via Moscow for validation before arriving here at the CSG.
Premier allumage de l'étage frégate.
And he's just announced that we've had the switch on of the frigate upper stage engine. That's what it looks like up there. Frigate is that gold structure. That's what's left now of our launcher. And it's switched its engine on. So we're really starting the next phase now of the journey. The frigate upper stage is a little bit like a taxi driver. It's taken the wheel, and its job is to deliver our satellite to its drop-off point in space. We call that special place the separation orbit. The guests here watching the launch from the Mission Control Center. Now, if we just take a look on the right-hand side, you can still see the image of the frigate upper stage. So we're looking here, the gold structure frigate. In the middle is the dispenser, and then on the left-hand side we could see our satellite. And there you can see on the right-hand side our trajectory on the top, and our flight path, if you like, a sort of a visualization of where we are on the planet. We're in the range of the tracking station of Bermuda. We're flying out across the Atlantic, heading north towards our next tracking station, which will be the St. Hubert tracking station. That's in Canada. That's going to be the next tracking station to pick us up. And the CSO satellites are the orbital space component of a program called MUSIS. We'll be finding out more about that later. But in the meantime, the satellites will replace the French Armed Forces Helios satellites. And they are high-resolution. The CSO satellites are high-resolution reconnaissance satellites, which will give the military detailed images of what's happening on the ground. And the CSO program is for the French Ministry of Defence's procurement agency, the DGR. We're going to hear from them now.
Today, military space applications are clearly vital for assuring our independent strategic decision-making capability and the conduct of military operations. That's why the defence spending plan for 2019-2025 intends to devote a significant budget to them. In 2022, we're going to renew most of our military telecommunications satellites, signals intelligence satellites, and of course our observation satellites, as we're already doing with the launch of CSO from French Guiana. We'll then be orbiting 2 more CSO satellites, the third of which is planned to launch on the new Ariane 6 vehicle in development. Starting in 2023, we're also going to prepare the successors to these satellites, particularly for signals intelligence, but also for observation. We'll begin building all these systems, including the third telecommunications satellite. And we'll be complementing our capabilities through this defence spending plan with geopositioning assets. For that, we'll be using the European Galileo system for a program called Omega. That program will give our forces a satellite positioning capability independent of the US GPS system. We obviously want to pursue this effort under our defence spending plan with our European partners, and we're going to ask them to join us on all of these programs wherever possible.
And during that film, we heard from the range operations manager that we have confirmation that we've now flown into the range of the St. Hubert tracking station, or Saint-Hubert, which is in Canada. So the guys and girls there have picked up our signal. They're tracking our launcher as we speak. And the town of Saint-Hubert is just outside Montreal in Quebec in Canada. And the aerospace industry, I believe, is very important there. Apparently the Canadian Space Agency has its head office in the borough, so we're heading off now over the northern hemisphere towards the North Pole. Heading out over Greenland, and we'll be coming down the other side of the Earth. CSO is very much a French national programme, although the services will also be available to some of France's partners. So it's logical that the French Defence Procurement Agency, who we heard from just now, the DGA, chose the French Space Agency as the contracting authority to provide both the satellites and the launch services. In fact, the French Space Agency is actually called CNES in France, which stands for the National Centre for Space Studies. And as I said earlier, teamwork is responsible for an awful lot of things in space, and the CNES has been responsible for many important and exciting space programs over the years, always with teamwork. And since its inception in 1961, it's been working with the Ministry of Defence in the field of space surveillance and tracking. Very important work there. Let's go over to the CNES now for more on their space defence systems and the CSO programme, as well as their broader range.
The launch of this first CSO satellite is a key milestone in our military space strategy that highlights the three facets of how CNES is serving defence applications. First, CSO draws on the heritage of everything we've developed since 1986 with the Spot, Helios and Pléiades satellites, and we'll continue to do that since we're now working on Ceres and the next generation of Syracuse. Second, CSO illustrates all that is best about France's space technology capabilities. CNES, in partnership with the French space industry, has developed the marvel of technology that is Cso1. And I believe we can say it is the envy of the world. And third, this evening's launch is only a start, as CNES's undisputed expertise will be supporting a whole series of operations once the satellite has been sent aloft and then begins its service life. All of this will show how effectively CNES is supporting our defence community.
Wonderful, isn't it? Some really fantastic programs there. Really high-tech and very, very exciting work that's being done by the men and women in the space world. And here we are looking at these beautiful images of our satellite attached to the upper stage there. We saw them. Look on the right-hand side of the screen. You can see it there. Just a quick description of what we're looking at. The frigate upper stage to the left, which is burning its engine. It's a circular structure with 6 spherical tanks, 4 of those for propellant, and 2 of those for avionics. That's the kind of thing you find on the aeroplane, the flight control systems, navigation, that kind of thing. And then you can't see it very well, but in the middle is a sort of a round circular disc structure, and that's the special adapter, or dispenser as it's sometimes called, which is attaching our satellite. And then in the front, the white structure is our satellite, Cso1, and it's got 4 solar panels. You can see 2 of them there, all nicely and neatly folded up. Those are going to unfold later when the satellite is separated. Now, these CGI images that we're looking at are a simulation of what's actually happening up there in space. So obviously it's not the real thing, it is a simulation, but basically what happens is the experts plan an incredibly detailed program of events which they then put into the computer, and the computer then generates these lovely images for us to be able to see, and you get a really good view of it there because you can see the frigate upper stage from behind. And basically every movement, every white flash, every burn of an engine that you see is what has been scheduled to happen at this moment in space. And I think those little white things that we can see there may be the nozzles which help the frigate upper stage to move around. We'll see this later in the flight, but it does lots of orientation maneuvers. And it gives little bursts of gas, I believe. Do correct me if I'm wrong with that, but I think that's the way it maneuvers itself. So as it twists around, we get a great view there of the satellite. It's getting ready now to...
Première section du frégate.
I was about to say it's getting ready to switch its engine off, but it's actually now done it. We have that confirmed from the range operations manager. So the onboard computer has sent the command to switch off the engine. It knows because of various things. It knows where it is in space. It has times, etc. It knows when to switch its engine off, and it's now done that. So we're really entering the next phase now. It's called the ballistic phase. Ballistic means travelling without the engine. We're coasting, travelling without propulsion. We're coasting without the engine. It's quite an interesting word, actually, because ballistic, I did a little bit of digging, apparently comes from the Greek word to throw. And it actually takes its name from a Roman weapon, which was called a ballista, or sometimes called a bolt thrower. And that's because ballistae looked rather like large crossbows, and Roman soldiers used them to hurl large rocks over great distances to try and damage rampart walls. And it's been said that the whirring sound of a ballista-fired stone would strike fear and dread into the hearts of those inside the besieged walls. Over now to find out more about our satellite, Cso1.
In the domain of national security and defense, space assets give France an independent situational awareness and decision-making capability while boosting operational effectiveness. They are vital to the conduct of military operations. Hundreds of operators use imagery from our military satellites to do their job every day. More than 50 satellite telecommunications stations are deployed every year to link mainland France to theatres of operations. Nearly two-thirds of weapons are fired at targets located from satellite images and guided by a satellite-based positioning system.
The renewal of armed forces starts here.
The 2019-2025 Defence Spending Plan reaffirms the importance of space and provides the resources to completely renew the nation's military space capability. This renewal cycle gets underway with the launch of the first CSO satellite in December 2018, leading off the new generation of military observation satellites designed to meet the armed forces' growing needs. The constellation of 3 identical satellites will be deployed by 2022, replacing the Helios 2 satellites currently in service.
Space-based observation is designed to complement ground, surface and air systems and assist in detecting, locating, reconnoitring and identifying any military target of interest, as well as to generate data for intelligence, targeting or geography. These missions are accomplished day and night in all weathers and all around the globe, within timeframes geared to the pace of operations.
The CSO optical constellation has been developed in close partnership by DGA and CNES for distinct operational missions.
The first mission is reconnaissance, performed by 2 satellites orbiting at 800 kilometers to enhance coverage, acquisition and revisit over theatres of operations. The second mission is identification, performed by a 3rd satellite at 480 kilometers to deliver the highest possible resolution and detail of analysis. For these missions, the satellite's telescope acquires imagery in the visible and infrared, using a variety of viewing modes to cover a broad spectrum of requirements.
The satellites are operated by CNES from Toulouse, where it positions and keeps them on station, draws up their work plans and conducts image quality control. The armed forces can order and receive imagery from different sites in mainland France and directly from the theatres where they are needed. The CSO satellites combine the very best of French industrial expertise, giving the armed forces a key technological edge to gain military advantage.
CSO offers numerous improvements. First, better precision with imagery of unrivaled quality in Europe, thanks mainly to its large telescope. Second, more capacity, with more images acquired per orbit and per day. And above all, greater agility. This extra agility means more images can be acquired when flying over a particular area of interest. And third, improved responsiveness, with the ability to downlink images from the satellite to a ground station near the polar circle in Sweden. This significantly shortens the time from request to delivery.
The CSO satellites are part of a broad program called MUSIS that will also be assuring continuity of service in radar satellite imaging to sustain a complementary all-weather capability.
This additional capability is currently provided by bilateral cooperation agreements that give France access to data from the German SAR Lupa and Italian Cosmo SkyMed systems. For MUSIS, similar cooperation arrangements are in place to secure long-term exchange of data from CSO and the new generation SARA radar satellite for Germany and second generation Cosmo SkyMed for Italy.
The CSO system is also open to other partners. Sweden and Belgium have already joined the CSO community, and France is actively engaged in discussions with other nations to extend it and consolidate Europe's space intelligence capability in the years ahead. With CSO, France is acquiring a capability like no other in Europe, tailored to its forces' needs. This system will initially complement the existing capabilities offered by Helios 2 and Pléiades, bringing extra resilience to new threats.
As the President has stated, space is a matter of national security. Our military space capabilities deliver vital support to our authorities and military operations. They are an important element of France's strategic independence. With the arrival of new threats, it's crucial that we maintain our ability to surveil, identify, know and act from space and in space. In this context, the launch of CSO marks a key milestone in the renewal of our military space capabilities.
Very exciting and very inspiring. Now, just to let you know, we've gone out of the range of the tracking stations, so we're in a period for about 31 minutes of being out of the range of the tracking stations, all very much part of the plan, and that's why we don't see the details on the bottom of the screen giving us the information, because we're not receiving the telemetry at the moment, and that's all perfectly normal. The Soyuz vehicle is storing the information, and when we check in again at the next telemetry station, it will be scheduled to download that. Now, spacecraft have lots of jobs, as you well know. For example, things like telecommunications, internet, saying hello there to the camera. Team's looking very relaxed there. Of course, they're extremely experienced. They've all done this many times before. And then other jobs of satellites and spacecraft, well, things like looking deep into our universe, trying to understand who we are and where we've come from, travelling out into the solar system to land on other planets, and even try and bring some home. And of course, looking back at Earth to understand our own planet. We call that Earth observation, and it's hugely important, because you can see things from space that you can't see from Earth. So space plays a vital role in monitoring things like the ice caps, the oceans. And it plays a hugely important role, of course, in the military. Let's take a look at the history of military observation from space.
Military observation is vital to inform the decisions of chiefs of staff. In the First World War, highly vulnerable captive balloons and later dirigible airships were gradually replaced by aircraft. These aircraft were equipped with photographic cameras. During the course of the 20th century, techniques began to improve, enabling automation of photographic observation from aircraft in the visible and infrared. The first drones also began to appear. Then came the era of satellites, able to view any point on the globe and acquire wide area imagery. Following the first American and Russian spy satellites, France launched its Earth observation program, first Cso1 in 1986, offering a resolution of 10 meters, and then Cso2 and Cso3. Helios 1A, its first military satellite, was launched in 1995. In 1998, Cso4 brought the capability to image relief. Helios 1B was launched in 1999. Performance continued to improve. In October 2002, Cso5 offered a resolution of 2.5 meters and a high-resolution stereoscopic instrument. Then came Helios 2A in 2004 and Helios 2B in 2009. Today, France is the European leader in optical military space observation. Finally, the Helios constellation was complemented by the dual-use Pléiades satellites launched in 2011 and 2012, for which the armed forces have tasking priority. Now all is set for Cso1 in 2018 and then Cso2 and 3 by late 2022.
Indeed there. So going back through the different satellites which have been launched for the military, bringing us up to today, the beginning of the CSO program with the launch of Cso1. And of course we've been hearing that the constellation will eventually consist of 3 satellites with 2 different missions from 2 different orbits. So Cso1 is part of the reconnaissance mission. It's extremely high-resolution images from an orbit of 800 kilometers above our Earth. That's where we're heading towards now. Then Cso2, which is scheduled to launch in 2020, that's going to fly over 300 kilometers lower than its triplet on an orbit of 480 kilometers above Earth. And its mission is a bit different. Its identification is going to be providing high-resolution images and giving a huge amount of detail. And then the third triplet is Cso3. That one is going to be launched, hopefully scheduled for 2021, and it's going to join its elder, Cso1, in the reconnaissance orbit, back in the 800 kilometers above Earth orbit. And its job is to improve the revisit time in all the points of the globe. Now, due to CSO's location in space, Cso1's location in space, 800 kilometers above Earth, it's been given some unique ability. In fact, it's a first technologically. Let's find out more.
To counter the perturbing effects of Earth's environment, a satellite must regularly perform trajectory correction maneuvers to maintain its orbit. Until now, such maneuvers were controlled from the ground and forced operators to interrupt the satellite's mission.
CSO is the first operational observation mission ever able to decide on its own how it needs to maneuver in response to the trajectory information received from its navigation system. This unique embedded intelligence capability was made necessary by the high rate of orbital decay at 480 kilometers. The residual atmosphere at this altitude slows the satellite, causing it to lose several hundred meters every day and forcing it to maneuver often. On a part of the orbit where the satellite isn't acquiring imagery, for example over the oceans, the satellite's flight software initiates an altitude correction maneuver in the plane of the orbit. The satellite pitches to align itself in the desired direction and fires its thrusters. The thruster burn only lasts a few tens of seconds, enough for the satellite to raise its altitude, recover its nominal position, and continue imaging.
Autonomous orbit control is a major technological innovation that is the result of a huge engineering and validation effort. Orbit correction maneuvers are now transparent to tasking teams. This new capability will deliver real added operational value for the system's military operators.
So a very clever satellite, Cso1. Its special ability to correct and control autonomously its own orbit. So we are injecting Cso1 into what we call a sun-synchronous orbit. You've probably heard of that, or heliosynchronous orbit. But what does it actually mean? Well, it means that the satellite passes over any part of the Earth at the same local time each day, and that's very useful for Earth observation satellites because it makes communication and various forms of data collection very convenient. And that's because the satellite has constant sun illumination due to its inclination and its attitude. And of course, for a satellite that's taking images, the consistent lighting is very, very useful. It's one thing having satellites sending data down to Earth. It's another thing getting that data to the people who need it. You can just imagine how much information comes down from satellites. And it all has to be sorted and processed. And it has to be made available to the users in a user-friendly way. And collecting that data, sorting that data, processing that data is a huge job. But of course, a terribly, terribly important one. Here's a little guide now on how to use the data from the CSO satellites for those people on the ground who will be using it.
Three main entities are involved in acquiring and distributing CSO imagery to users. The main user center in Cso1, connected to partner user centers, this center has a direct receiving station. The control and mission center in Toulouse, and a polar receiving station in Kiruna. Each user center collects and ranks acquisition requests from military users and units in the field. These requests are then forwarded to the mission center via the nerve center in Cso1, the gateway to the CSO system. The mission center establishes the satellite's work plan for the next day, sharing capacity between international partners. This plan is uplinked to the CSO satellite via the station in Kiruna. The satellite executes the work plan and downlinks imagery acquired to one of the 2 receiving stations within range. After processing of the data in Cso1, the imagery is sent out to user entities. Exceptionally, the system has the ability to alter the satellite's work plan at any time to meet urgent requests, adapting to the needs of users in different theatres. The system can also accommodate new European partners, supporting the deployment and ramp-up of the CSO constellation.
And you can really see there, can't you? If you remember, I said earlier that space programs are so much a question of teamwork, and all these people across the planet all pulling together to make this work and to make this happen. And satellites are important, obviously, for helping the men and the women in the armed forces in their military operations, because they are very much depending on each other and the information that they're getting through. Arianespace plays a very important role in getting those satellites into space, and Cso1 will be the 69th satellite to be launched by Arianespace for military use, and will also be orbiting Cso2 and Cso3, of course, the 3 triplets in the constellation. The third one will be actually on board the new heavy lifter, Ariane 6-2, so that's going to be very interesting and very exciting. It's vital for the military to know what's happening at any time of day and night, and Cso1 can do just that because it has day and night acquisition. It can provide very high-resolution imagery in both daylight and in the infrared, so that is important. And even though the CSO satellites are French, their data will also be accessible to their European partners. So those are in countries like, for example, I believe Germany, Sweden, Belgium, and I also think Italy. Good pictures there of our satellite. There it is attached, going to be providing that vital information to the French military, which considers space to be an important part of their security.
Satellite imagery supports a broad spectrum of missions whose common goal is to sustain the rate of operations. This can be illustrated by 3 specific examples. Intelligence. Satellite imagery is a precious aid to obtain information about zones that other sensors can't reach. In particular, it helps to gauge the strength of forces present or the level of activity at a site under surveillance. Targeting for airstrike planning. Prior to a strike, satellite imagery is used to precisely geolocate the target, supply the parameters required to guide the missile and reconnoiter the immediate environment in detail to avoid collateral damage. It then serves, as here, to assess the effectiveness of the strike by comparing images acquired before and after the operation. Production of geographic data. Very high-definition maps of strategic zones enable the exact nature of the geographic environment to be determined before forces are deployed. Here we can see very fine details of a town being used to plan an aerial reconnaissance mission ahead of sending troops on the ground. Digital terrain models are also generated on request from Pléiades or Helios stereo imagery, and soon from CSO, when those in the Spot 5 database offer insufficient resolution. Such products can be used by certain weapon systems. The agility, resolution and responsiveness of the CSO system will greatly enhance product performance for these 3 applications.
Looking here at the Space Center, the Guyana Space Center back there, and here in the Mission Control Center, the team's looking very relaxed. As I said before, they've done this many times and they are extremely experienced. 41, coming up to 42 minutes into the flight of Cso1 to its orbital slot in space, getting closer. It's flying on board what remains of the Soyuz vehicle, the frigate upper stage. We're in what we call the ballistic phase. We're cruising without the engine. And we're outside the visibility of the tracking stations at the present time, all perfectly planned. You can see our flight path there. Rather lovely image of the Earth turning. We lifted off from South America. We headed over the North Pole, over Greenland, and coming back down the other side of the planet now towards southwestern Australia. As I said, we're outside the tracking stations, but the next one that will be picking us up is New Norcia. And to get there, we'll be flying over Southeast Asia and heading down there over the Pacific. And that's what it looks like up there. Every satellite is made by a group of industries working together. It's called a consortium. And Cso1 was built by a consortium led by Airbus Defence and Space.